Hi, good morning. Good morning. Right. People online, hello, good morning. Good morning. Are there any questions for homework? This is from gravitational field. Right. What are the questions for homework? $40? Okay, 46. We have done part A. Right. Question 46. The part A we have done. Part B says it is claimed. It is claimed a satellite. Yeah.
So today are we going to do only past paper or are we going to do notes also?
Sorry, I can't. Okay.
Are we going to do notes today only or only past paper?
No, both.
Okay.
Guys, last class I gave you a notes tube, right? Theory difference. Got it? Right. It is claimed that the satellite is in orbit at a height of 8.5 into 10 to the power of 5 meters would make 15 orbits of the Earth every 24 hours. In 24 hours, it makes 15 orbits. Assess the validity of this claim, and it's a pi marker. Okay. So we'll begin with once again. If P equals in, if is GMM over R square, and into A is R omega square, where simple M is the mass of the satellite and capital M is the mass of the central object, which is Earth in this case. Okay, it's the satellite is orbiting the Earth. So the simple length will cancel out. GM equals R cubed. R into R square is R cubed. Omega, I will replace it with 2 pi over T square. GM equals 2 pi square is 4 pi square R cubed over T square. So T square equals 4 pi square R cubed over G. I can use this equation to find the time period and show that 15 of those will be approximately equal to 24. Correct? So, mass of the Earth is given, radius of the Earth is given, and this says this satellite is at a height of 8.5 into 10 to the power 5 meters. Okay, from the Earth's surface. It is claimed that a satellite in orbit at a height of 8.5 into 10 to the power 5 meters. At a height of, So t square equal 4 pi square r. R is going to be a radius of the earth, which is 6.36 into 10 to the power 6. 6.36 into 10 to the power 6 in meters. That is the radius of the earth, plus 8.5 into 10 to the power 5. That will be the distance from the center of the earth to the satellite. And that needs to be cubed, r cubed, over g, 6.67 into 10 to the power minus 11, into m, the mass of the earth, 5.98 into 10 to the power 24. This gives you the t square. Get the square root of this. That will be the t. I'm getting 6090.7 seconds. In seconds. This is the time taken for the satellite to go around the earth. Just one circle. So the question is, it is claimed that a satellite in an orbit of this height would make 15 orbits of the earth every 24 hours. 15 orbits. So let me see how many orbits it makes in 24 hours. Number of orbits in 24 hours. That is going to be 24 multiplied by 3600 to convert 24 hours to seconds. Divide by the time taken for one orbit, which is 6090 seconds. That's about 14.2, no? So the statement says it makes 15 orbits of the earth around every 24 hours. Acceptable. Close enough, no? Statement is. Yeah, after you get up to here, you have already got your marks, if I'm not mistaken. Whether you say yes or no, both are okay. One can say yes, 14.2, close enough to 15. Another person can say 14.2, no, it's not 15. That doesn't matter. Okay. So just make a statement. 83. Right. It is suggested that, okay, it is suggested that the satellite could be placed in an equatorial orbit at a radius of 42,200 kilometers. With this radius, the satellite would have an orbital period equal to 24 hours. Okay. Give one advantage and one disadvantage of placing a weather satellite in a polar orbit rather than in a suggested equatorial orbit. Okay. Guys, have you heard of something called geostationary orbit? Geostationary satellites. Have you? What is a geostationary satellite? Yeah, so geostationary satellite is placed above the equator and it rotates in the same direction as the Earth and rotates in the same angular velocity as the Earth, or the same time period as the Earth. So for a person who is living in the equator, at the equator, and if he can see the satellite, he will be able to see that satellite every day at the same place. Like you are rotating, right? The Earth is rotating. Same way that satellite is also rotating with the same angular velocity. So for a person who is at the equator, if he can see that orbit, if he can see that satellite tonight, he will be able to see it next week also at the same place. For him, it looks like okay, the satellite is not moving. Okay. For him, it looks like the satellite is not moving. But the truth is, with respect to space, both are moving in the same direction, same angular velocity. So, with respect to the Earth, with respect to the observer at the Earth, it looks like that satellite is not moving. That is what you call it geostationary satellite. With respect to the Earth, it looks stationary. Okay, but nothing is stationary. So they are talking about a satellite like that. It is suggested that the satellite could be placed in an equatorial orbit at a radius of 42,200 kilometers when you place it at this distance with a radar. The satellite would have an orbital period equal to 24 hours. So that will also have the same orbital period as the Earth, which is a geostationary orbit, which is a geostationary satellite. So the question is now, give one advantage and one disadvantage of placing a weather satellite in a polar orbit rather than in a suggested equatorial orbit. What is the benefit, advantage of putting it in a polar orbit? Polar orbit, the satellite rotates in this direction, and it has a height of only 8.5 into 10 to the power 5 meters. That is comparatively much closer to the Earth. 8.5 into 10 to the power 5 is about 850 kilometers. Okay. So it is closer to the Earth means definitely it will make multiple. It will make multiple rounds in a given period. That is an advantage. Correct. That is an advantage, and also it will be able to monitor more points on the Earth because it is rotating. Okay, with respect to the Earth, its position is changing. So it can check the weather condition. This is a weather satellite, right? Yeah. It can get details of multiple points of the Earth. That is an advantage. What is the disadvantage? What do you think is the disadvantage? Locating it. Compared to a geostationary orbit, for a geostationary orbit, you know where it is. So that problem is not there. There is an advantage about the geostationary orbit. Locating it is not a problem. But if you take a polar orbit, its position keeps on changing its time. So locating it will be a difficult task. That is a disadvantage, right? It's a two marker. The advantage, it can collect details. It can collect details about much more points on Earth.
Can you tell the answer?
Can collect details about. It can collect details about much more points comparing to a geostationary satellite. Okay, so the disadvantage you can write. Locating the satellite will be difficult since its position keeps on changing. Okay, what's next? For the seventh one, it's a small question. Electrostatic forces and gravitational forces can both be modeled by the idea of a field. Give one similarity and one difference between the electric fields and gravitational fields. So there's a gravitational field. If you remember, you take a mass, the gravitational field around it is always towards it. Because the gravitational forces are always attractive. Whatever the object that you keep around this mass, it will experience an attractive force. So gravitational fields around an object will be towards the object. Right? But if you take an electric field, if I take a charge, if I take a positive charge, the electric field lines are away from it. Do you remember that? If you take a negative charge, the electric field lines are towards it. That is the predominant difference between the gravitational fields and the electric fields. The gravitational field lines are always towards. Electric field lines can be either towards or away depending on the nature of the charge. That's the difference. The similarity is both are radial. Both are directed towards a point. Okay. That is one similarity. And also you can say both varies according with the distance with the inverse square law. The further you go away from the object, the strength of the field reduces. Right? Gravitational field is given by gravitational field strength at a point is given by G over R square. Correct. Electric field strength is given by 1 over 4 pi epsilon naught Q over R square. Both are connected to that over R square. Both electric field strength and gravitational field strength are inversely proportional to the square of the distance. That can be considered as a similarity. Understand? So the question asks you only for one similarity and one difference. I will give you a few. You can think of, remember a few of those. So write the similarity. Both fields are radial. That space might not be enough. You can write here. This space you can use it for that. Similarity. Both fields are radial. That is one similarity. The next one.
So both fields are
Radial. Radial means direct. Concentrating towards a same particular point. Okay, both fields are radial. Full stop. The next one. Strength of both fields. Strength of both fields follows the inverse square strength of both fields follows the inverse square root. Sorry. Follows the inverse square root. Sorry. Okay. Right. Differences, right? Gravitational field lines are always directed towards the object. gravitational field lines are always directed towards the object. Gravitational field lines are always directed towards the object. Comma. Electric field lines can be either towards or away from the object. Couldn't get the tip. Did you get the tip? Okay, what's next?
The electric field lines are
Electric field lines can be either towards or away from the object. $53 and what else? Right, we'll come back to this a bit later. We'll do a bit of theory.
The only difference from it.
One is associated with the mass, the other one is associated with the charge. Yeah. So that can be considered as a difference. Okay. Right, as we started off with astrophysics last class. You got this too? Who did get this too? The theory too? Okay. Right. So I think we spoke about what is black body radiation last class. No? We discussed up to this point, just the first page.
So did you check the video I sent in you in the group?
So, guys, I'm very bad with this WhatsApp. I mean, I'm
I
very
was
bad
talking about that black paint. You didn't answer what I was saying, so I sent you a video.
I wouldn't have opened it in the first place. I still have about 140 messages, 100 messages. Okay. So it will take some time.
It will be the last message anyways. Last link.
Right. So we spoke what is, we'll start with that black body radiation again. A black body radiator is a theoretical body which completely absorbs all the radiation that lands on it. We can imagine a cavity with a tiny hole in one side, and the hole itself is a black body. It is considered to absorb all the radiation that lands on the hole as it goes into the box and bounces around with no chance of escaping out the hole before it is absorbed inside the box. No radiation is reflected, hence the name is given for it is black body. So basically, a black body is something which completely absorbs all the radiation that falls on it. So then, can you see? You can't see. I told you about it last class. The reason why you can't see it, for you to see something, there should be light reflecting on it. Okay? So, if there is absolutely no light which is reflected from the object, you can't see the object. Or you can see me, the light falling on me is reflecting and it's passing through your eyes and it goes to your brain. The message is going from your eyes to the brain. The brain reads it as, okay, this is this That is how humans we are designed. Okay. So now if you take a black body, if you take an object, when the light falls on it, if electromagnetic radiation falls on it, if it is 100% absorbing it, if it doesn't give a single percent out, that means you can't see it. Okay? Can't see it. So that's what makes it a black body. Completely absorbs all the radiation. Fine. All objects, the next page, all objects emit electromagnetic radiation. All objects emit electromagnetic radiation. Infrared cameras can detect radiation from our bodies. Okay? But with our eyes, we can only see visible electromagnetic radiation from hot objects. For example, the red glow from a fire. We can see only the visible light. We know that good absorbers of radiation are also good emitters. So a black body radiator is considered to be a perfect emitter. So if a black body is a perfect absorber of radiation, on the other side, it is also a perfect emitter of radiation. It will emit EM radiation at all wavelengths, all the wavelengths. And how much of each wavelength will depend on the black body's temperature, depending on the temperature. How much each wavelength will depend on the black body's temperature. The Stefan Boltzmann law. Okay. How bright is a star? With the naked eye, we are only able to distinguish 6 different levels of how bright stars appear to us. This is insufficient for us for scientific use, as many stars of differing brightness would appear identical to our eyes. Astronomers therefore use a more precise measure to classify the actual brightness of stars, their output power, which is known as luminosity. Okay. So luminosity is something to measure the brightness of stars. Astronomers therefore use a more precise measure to classify the actual brightness of stars, their output power, which is known as the luminosity. We define luminosity as the rate at which energy of all types is radiated by an object in all directions. This depends upon both the object size and, more importantly, its temperature. Okay. Highlight that part. Luminosity as a rate at which energy of all types is radiated by an object in all directions. That's luminosity.
So, black body is just a theoretical model, right? Like, it doesn't practically exist, right? Like,
It is
practical. It can't be that perfect, right? Like, that's spot on. Like, it has to have some degree of incidence, like, where it's like,
there is black body.
that can occur in nature.
Not definitely not on the Earth, but in space, yes. We will be speaking about it towards the latter part of this.
So, but for example, superconductors are there. They don't activate, right?
Okay. But black bodies, yes. As currently, yes. Maybe there can be theories which can break down it in the future. But at the moment, yes.
So I mean, like,
Yeah, I understand what you're saying, but yes, 100% absorbing black bodies are there. That is the reason we will be speaking about something called the ultimate fate of universe. Have you heard about it? I mean, now I told you guys last week. Now when I started this topic itself, I told you have different beliefs. Okay, so I will speak about the science perspective. Okay. So what I speak here is nothing to do with your beliefs. You can continue whatever it is. You should be having an ultimate fate. I mean, ultimate fate of the universe. Different religions have different beliefs. But according to science, still there is no ultimate fate. There are 2 possibilities. Okay? Either, yes, correct. So either it can keep on expanding, the universe can keep on expanding forever. or the universe can keep on expanding up to a certain point, and again it can start compressing. Okay, so which one of the two will happen is not decided yet. Why? That is because of the black matter. There is something called black matter in the universe. We will speak about it later. So no one knows still what is the mean density of the universe. The average density of the universe is you don't know, because how much black matter is there is no one can still find that. So whether the universe is going to keep on expanding forever, or it will expand to a certain extent and it will compress after that, will depend on the amount of black matter in the universe. Okay, so that black matter you can't see, but it is there. There is proof that it is there. Okay, getting back to the point, we define luminosity as the rate at which energy of all types is radiated by an object in all directions. Okay. This depends upon both the object size and, more importantly, its temperature. The electromagnetic radiation is emitted across. Electromagnetic radiation is emitted across a very large range of wavelengths. A perfect black body radiator will emit energy across the entire electromagnetic spectrum, following a distribution like those in figure D. This distribution is given by Stefan Boltzmann law. Stefan and Boltzmann are two people. Their law is this. This tells us that the output power from a black body is proportional to its surface area and the fourth power of its temperature in Kelvin. The luminosity is proportional to its surface area. So L is proportional to its surface area A, and also to the fourth power of the surface temperature in Kelvin, which is T to the power 4. So putting both together, you get this equation. L equals sigma A to A T to the power 4. L is the luminosity, A is the surface area, T is the temperature in Kelvin. So guys, this sigma is a proportionality constant, where the Stefan Boltzmann constant, this sigma is known as the Stefan Boltzmann constant, which is 5.67 into 10 to the power minus 8 in terms of SI units. Is that okay? For a sphere, this would become L equal 4 pi r square sigma T to the power 4. Why? What is the surface area of a sphere? 4 pi r square. You all did your grade 9 maths, right? Area of a circle is pi r square. Surface area of a circle is, the sphere is 4 pi r square. So if you replace this A with 4 pi r square, then you will be getting 4 pi r square into sigma into T to the power 4, where r is the radius of the sphere. Is that clear? Highlight the two equations.
So can you finish the class at 11 and without a break?
Let's see. Don't think so far. Go with the flow.
So because yesterday I came home at 1, slept at 1:47. So
So
tired.
that is, so the others didn't come home at 1. That's
Okay, sir. But others don't have to wake up at 6:30, no, so there should be a
Okay.
bit of
Right.
advantage.
Guys, there is a worked example. You can have a look at it later. Turn to page number
So
5.
L is output power, right?
Luminosity.
Then why did you say output power is proportional to area and
There is a luminosity. So luminosity is the output power actually. Yes, the rate at which the energy is transferred. It will be watts per square meter. No? It will be in watts. Yes. It's power. Here's page 5. Question 1, can you give a try? So very straightforward question. What is the luminosity of the star Sirius, which has a surface temperature of 12,000 Kelvin and a diameter of 2.2 million kilometers? 2.22 million kilometers. Give a try. Are you getting this answer? 1.82 into 20. They have given the diameter in kilometers. So multiply by 1000 to make it meters and divide it by 2 to get the radius. No? That you can use as a radius and put it into this equation 4 pi r square into sigma into e to the power 4. You'll get the answer. Is it the answer? Right. Right. Let's turn to page 4.
So what about the second question, sir?
Patience. Patience. Right. Page 4. Beam's law. To calculate luminosity, we need to know the temperature of the star. There are various methods for determining the temperatures of stars, but we will focus on one that uses the wavelength of light given off by a star. when we examine the range of wavelengths emitted by a star known as its spectrum, we find that some wavelengths are given off with more intensity than others. Some wavelengths are given off with more intensity than others. So if you look at intensity versus wavelength, it looks like a graph like this. Okay, so there is this wavelength which has the highest intensity. So this is a special point we speak about it. We saw from the Stefan Boltzmann law that as the temperature of a black body increases, it emits more energy. Shows how the amount of energy emitted at different wavelengths changes with temperature. At higher temperatures, the curve has more pronounced peak, and the wavelength of the peak output gets shorter as the temperature rises. The relationship between the peak output wavelength and temperature is described by the Wien's law, which is this lambda max into T is inversely proportional. Lambda max is inversely proportional to the T. Okay. So that lambda max is inversely proportional to T means you can write it as lambda max is equal to the proportionality constant K into 1 over T. So which means lambda max into T is a constant. That constant, this constant is known as the Wien's constant. The Wien's constant. So that lambda max into T is equal to the Wien's constant. That constant value is 2.898 into 10 to the power minus 3 in terms of SI units. 2.898 into 10 to the power minus 3. Okay, this number is known as the Wien's constant. So that is a special number. Wien constant will be given. Highlight that equation. Lambda max into T is equal to this. Okay. Right. Guys, copy down this one. Show this part. Lambda max is inversely proportional to the Kelvin temperature. You get lambda max into T is constant, which is the Wien's constant. Okay. Now go back to that graph on page number 2. You will see 3 graphs. Okay. Now when they have given 3 graphs here, all 3 graphs are having 3 different temperatures. The one in red is 6000 Kelvin, star of 6000 Kelvin. The one in blue is 4500 Kelvin. The one in green is 3000 Kelvin. And you can see as the temperature of the star is increasing, that peak point is going shifting to the left. Can you see that? Green is 3000 Kelvin. Blue is more than that, 4500 Kelvin. So the lambda max is to the left, lambda max is lesser. Red is even more, 6000 Kelvin. The lambda max is even further to the left. So higher the temperature, the lambda max will be lesser. What law is that? What law is that? Wien's law. Lambda max is inversely proportional to the thermodynamic temperature. So higher the temperature, lesser will be the lambda max.
So this is Maxwell-Boltzmann distribution, right?
Correct. So I'm talking about this one. Why is this peak shifting to the left? So when the higher the temperature, lesser will be the wavelength at which the intensity is maximum. That's lambda max. Lambda max is the wavelength at which the intensity is maximum. That wavelength will be shifting to the left as the temperature increases. Okay. Understood. Right. So on page number 4, there is a worked example. Looking at the spectrum of light from Betelgeuse in the constellation of Orion, its peak wavelength is 9.35 to the power minus 7 meters. What is the surface temperature of Betelgeuse? So you can use lambda max into T is 2.898 into the power minus 3. Wavelength lambda max is given 9.35 into the power minus 7. From that you can find what is the surface temperature. Okay. Right. Now on the next page there is another question. Question number 2. Can you do that? Couldn't get this. Can you get this? Right. The sun's surface temperature has been measured as being 5,800 Kelvin. Calculate the peak wavelength of the solar spectrum. Peak wavelength. So lambda max into T is the range constant, which is 2.898 into 10 to the power minus 3. So the T is 5,800 Kelvin. Lambda max into 5,800 is 2.898 into 10 to the power minus 3. So that will be 4.996, no? So which we can take it as 5.0 into 10 to the power minus 7 meters. This is a peak wave. Oh, that makes sense. Guys, now 5 into 10 to the power minus 7 meters means 500 nanometers. So if this data is correct, what's given in this question, the surface temperature is correct. That means okay, the most intense one that is coming out from the sun is the one with wavelength 500 nanometers. Okay, so that means you should see the visible light spectrum is 400 to 500, sorry, 400 to 700 nanometers. Am I right? Do you remember that? The visible light spectrum, red, orange, yellow, green, blue, indigo, violet, has a wavelength from 400 to 700 nanometers. So the one with the 500 nanometers, if you see that color, is the one with the highest intensity. Okay. Right. The part B of it says what? The peak wavelength from the sun is in fact measured at the ground level as being 470 nanometers. We found the calculation to be 500 nanometers. Okay. But when it reaches the ground, the peak wavelength from the sun is in fact measured from the ground level as being 470 nanometers. Why is the measured value different from the calculated value from part A? Why? Sorry.
So because there are many different mediums that it has to pass through,
And
right?
then
So then it can change, right?
not really.
Because it refracts when it goes from a vacuum to air.
Not
Yeah,
really.
that's what I said.
No. Mm, 470 nanometers. Energy loss. Okay. Then no. Why? Any different reason? What was the answer?
Changes with the light refracts from a vacuum to air.
Due to refraction. So the speed changes. Yeah, that could be the reason. V equals F lambda. Because when the light is going from one medium to another medium, the frequency doesn't change. But when it is speed will decrease a bit. So when the speed is decreasing a bit, yes, the wavelength can be decreasing a bit. So 500 nanometers by the time it reaches the Earth, it has come down to 470 nanometers. That makes sense. Yes.
I also
Okay, sorry. Okay, so you can take that as a reason. When it moves from vacuum to air, there will be a slight drop in the speed. So there will be a small drop in the wavelength. Okay. It's nothing to do with energy loss actually. Because the energy anyway, now here comes in photons. When the photon is coming, it depends on the frequency. Yeah, so it's not because of that. Yeah, so that's the thing. So here the wavelength has decreased. That's because of refraction. Okay. Then
So aren't you writing an answer?
I already gave the answer.
So I didn't hear, can you please repeat?
When the light enters from vacuum to air, speed decreases. Speed decreases. So the wavelength will decrease.
Thank
Okay. Right, there's how about page number 38. Right. The planet Captain B orbits Captain Star. Scientists think the conditions on Captain B could enable the long-term survival of humans. Part A. The spectrum of radiation emitted by Captain Star has a peak of intensity at a wavelength lambda max 8.12 into 10 minus 7 meters. Show that the surface temperature of Captain Star is about 3600 Kelvin. That's for a person who doesn't know the theory. If you read this, it will look like Latin. Okay? What the hell is this? But the theory behind it is very simple. What law is this? Which law? Matter of a minute, you get the answer. What do you get the theory here? Lambda max into T is equal to the Wien's constant. What is the Wien's constant? 2.898 into 10 to the power minus 3. So the lambda max is 8.12 into 10 to the power minus 7 into T is 2.898 into 10 to the power minus 3. From here we get the T. That is 3,568.9. 3,569 Kelvin. That's about 3,600. Okay, that is the surface temperature of the star, Captain Star. The distance from Captain Star to the planet Captain B is given. The intensity, i.e., of the light received at the Earth from the Sun is 1,380 watts per square meters. Show that the intensity of radiation received at from Captain Star is about 0.4 times, i.e., the radius of Captain Star is given 2.03 into 10⁸ meters. Okay. Give it a try. First, find the luminosity of the star. Yeah, I have taken 9 at it. Got it? I get a 0.42. 0.42 IE is what I have got. Guys, look at this. Right. Let me explain. It's a 4 marker, but it's easy 4 marks, isn't it? Now they have given the distance from this star, Captain star, and there's this planet called Captain B. Okay. Just like maybe somewhere else. Like how the Earth and the Sun. There are 2 stars, one star and a planet, Captain star and Captain B. The distance between them is given. And radius of the star is given. So what I first did is I found the luminosity of the star using L equals 4 pi r square sigma T to the power 4. That means at which rate is the energy radiated from this star. Okay, at what rate is the energy is given, luminosity. 4 pi r square sigma T to the power 4. So the radius of the star we know 2.55 into 10 to the power, 2.03 into the power 8, the radius of the star, into sigma is a constant. 2.03 into the power 8. Sigma is what constant? What do you call that constant? Sigma is Stefan Boltzmann constant. 2.03 into the power 8, that to the power is the radius, 5.67 into the power minus 8 is the sigma. And the temperature is 3569, that is the surface temperature that I found in the previous part. I have used that to the power 4. That gives you the luminosity of this star. Once again, the rate at which the energy is emitted. Okay. And then intensity, if you can remember your AS level, intensity is power divided by P/4 pi r square. The intensity from a source at a distance r, the intensity is given by P/4 pi r square. Further you go from the source, the intensity reduces. Am I right? Intensity by definition, it is the amount of power passing through a unit area, which is measured in watts per square meter. So if you want to find the distance, at a distance r, the intensity, it is given by P/4 pi r square. So I'm using that equation here. P is the luminosity. Luminosity is the power. So L/4 pi r square. To see what is the intensity at the given distance at that planet. So the distance from the star to the planet is given 2.55 into 10 to the power 3. Okay. So luminosity is what I calculated in the previous part. Over 4 pi. The R is the distance from the planet to the sun. That square, that gives me 583 watts per square meters. Okay. That is the intensity of that star at that planet. Okay. Then they want to do a small comparison with our Earth and the sun. On the Earth, the intensity received from the sun is given 1380. So they want to know what is the ratio. So this 583 divided by 1380 will tell you, give you the ratio between the intensity that is received at that planet over the intensity that is received on the Earth, which is I over IE is 583 over 1380, and it is 0.42. That confirms I equals 0.42 times E. IE. Is that okay? Any questions? Any questions? People online, any questions, anyone? Right, the next one. Is that you can try it for homework. Something to do with the gravitational field strength. Easy question, easy 5 marks. Please do it for homework. Right. Guys, page number 43, question number 25. Page 43, question 25. Gliese or Gliese, I don't know, is a main sequence star in the constellation Aquarius. The graph shows how the intensity of radiation I emitted from this depends upon the frequency of how with the frequency the intensity is changing. So show that the surface temperature of this is about this star is 3000 Kelvin. Now guys, usually we get lambda now. So for a change they have given frequency. Piece of cake. V equals f lambda. You know the f, you can find the lambda. Okay. So I see the peak intensity happening at a frequency of 3.2 into 10 to the power 14.
It's around 3.1, right?
Is it 3.1?
3.2.
Are the darlings? Yeah, did the grade 9 maths, right? Before coming to? So lambda equals COF. C is the speed of light, which is 3 into 10 to the power 8 over 3.2 into 10 to the power 14. That tells you what's lambda max. That's a wavelength at which the peak is happening, which is 9.375 into 10 to the power minus 7 meters. This is the wavelength at which the intensity is maximum. From there onwards, you know what to do. Lambda max into T is a constant. What is that constant? What's that constant? Means constant. The value is 2.89.
2.899 times 10 to the power minus 3.
As you want to remember this figure, today even in the night, in the middle of your sleep, you have to tell 2.898 into 10 to the power minus 3. Okay?
They don't give it the data.
It's given, but with the amount of questions that you are doing, how can you really forget this number? 2.898 into 10 to the power minus 3. So the lambda max is 9.375 into 10 to the power minus 7. That into T equals 2.898 10 to the power minus 3. This gives you the T. $3,091. Kelvin. That is the surface temperature. Yes. Have you got this? The next part. As a red dwarf star, the luminosity of these 876 should be less than 10% of the luminosity of the sun. Evaluate within the surface temperature. Suppose this state, radius of the star is given. Luminosity of the sun is given. Easy. Within the luminosity of this star is 4.46 into 10^24 watts. The statement says, as a red dwarf, the luminosity of this gauge should be less than 10% of the luminosity of the sun. So luminosity of the sun, 4.46 into 10^24 over luminosity of the sun is given 3.83 into 10^26 multiplied by 100 will tell you the percentage of this star's luminosity as a percentage of sun's luminosity. Which is 1.16% or 1.17%, which is clearly less than 10%. Yes, you can say yes, it supports. Yes, agree? And got 1.17%. You found 10% of sun's luminosity and show that this is less than the 10. But isn't this nicer? Doesn't this involve a bit of class? You show that exactly what percentage that. No? Is that okay? Any questions? Easy marks, 8 marks, easy. Right. Then How about page 49? Question 20. Very similar to the previous question. Do it yourself. Give your confidence. I'm getting 0.35%. What about you? So guys, there's nothing new in this. This entire 8 marks, we have done this already 3-4 times today. So lambda max into t is a constant, which is Wien's constant. I picked the lambda max from the graph given. Lambda max is at roughly about 850 nanometers, which is 815 to 10 to the minus 9 meters. That into t is the Wien's constant. That gives you the t, 3409 Kelvin. Correct? Yes, easy 3 marks. Then a website states the luminosity of Ross 154 is less than 0.5% of the luminosity of the sun. Evaluate whether this statement is correct. The radius of that star is given, and the luminosity of the sun is given. So the radius of the Ross is given means you can find L equals 4 pi r square sigma t to the power 4. Using that, you find the luminosity of that sun, that star, which is 1.34 into 10 to the power 24 watts. Correct? And then see what is that luminosity as the percentage of the luminosity of sun. I found it to be 0.35%. Statement is less than 0.5%. Yes, it is correct. Okay. Right. Part B. Scientists have observed an Earth-type planet in orbit around Ross 154. The radius of the orbit is 0.096 AU, astronomical unit. Calculate the time for this planet to make. Oh, you don't need to know what it is. It's given what is 1 AU in the question. Given 1 AU means 1.5 into the power 11 meters. Okay. Calculate the time for this planet to make one orbit of Ross 154. Mass of Ross is given. It's easy. We have done enough of those. Start with F equals mA. F is gmmOr square. M into A is R omega square. So the M's will cancel. Gm equals R cube. Omega is 2 pi over T. That square. Gm equals R cube 4 pi square over T square. Do we need to derive it? Yeah, but I don't know. I always derive it. It's better if you can. 4 pi square R cube over G. I need to check that. I can't remember. Okay. So substitute into this equation. Just someone check the marking scheme and see whether is there a mark given for this derivation. Otherwise, there's nothing to do for 3 mark also, just to substitute into this equation. I don't know if they have allocated 3 marks just to substituting into this equation. Anyway, I have done this in so many questions. You should be able to get this done in less than 30 seconds. It's not going to take you a minute. Okay. So guys, substitute into that 4 pi square. The radius of the orbit is 0.096 which is 0.096. 1 AU is 1.5 into 10 to the power 11. That's the R. And that Q. G is 6.67 into 10 to the power minus 11. The M is the mass of the central star. 3.38 into 10 to the power 29. This will give you the T square. Get the square root of that. That's 2.29 into 10 to the power 7. Sorry, 2.29 into 10 to the power 6. Seconds. Yeah. Have you got this answer? Confirm learn marks. Equating what? Okay. To show in this one, is it? Yeah, from here you can get this one. Yeah, correct. So there should be some reference from where did you get this one. Don't think so much, just get this, derive this 2-3 steps. Definitely you should be able to do it in less than a minute easily.
So are there any equations or anything you have to memorize in this lesson? Like that they do?
Nothing. Everything is there in the formula sheets.
You just have to remember that.
Correct. You want a break?
Yes.
Take a 15 minutes break. See you in 15 minutes.
No, sir.
It's a democratic country, so we go with the majority. Okay?
So this is not a democratic country. Mono.
But we are in a democratic country. No? Something wrong. Guys, did you all get this answer what I have got? Huh?
What you did today.
Yeah. Give the unit. Let's quickly get the answer to the page 51 question 29. No need. Keep it for later. You can do it, but keep it for later.
What's the standard can be?
Yeah, that's the reason I told you. Let's leave it for later. Here's mark this for homework. Page 60, question 34. Page 60, question 34. Page 76, question 42. Page 86, question 49. Page 98, question 56. Right, get back to theory. Page 6 from the theory view. The Hertzsprung-Russell diagram, HR diagram. You have made this for O levels if you have done Edexcel O levels. Cambridge O levels, no. And local O levels, I don't know. But if you have done Edexcel O levels, definitely you have made this diagram. The Hertzsprung-Russell diagram. But anyway, it's not a big deal. It's a very simple thing.
So now it's like the Cambridge Journal.
Yeah, no, this diagram is not there. Astrophysics is there. Okay. Astrophysics, there is a part of astrophysics. What I meant is this particular diagram is not there. Okay. If you plot a graph of luminosity against star temperature, okay, so luminosity against the star temperature to confirm the trend of table A. you will find that there is a general correlation. However, the more data you add, the more complex the picture becomes. We must also remember that the temperature measurement assumes the star behaves as a black body. And the luminosity is similarly often not as accurate as we would like. In general, luminosity has to be determined from a calculation that includes the distance to the star, and measuring the distance to the stars is by no means an exact science. Such a plot can give us some very useful insights, but is not a graph in the true sense. It is known as a Hertzsprung-Russell diagram, not 100% accurate data representation, but yes, to a great extent it will be accurate. So guys, so Hertzsprung-Russell diagram is a diagram where this y-axis shows the intensity, the luminosity, and here they have given as a ratio of the luminosity with respect to the luminosity of sun. This y-axis they have given relative intensity. You sometimes call it the relative magnitude. So this one means this is the intensity of what? The sun. Okay, it is the intensity of the sun. So here 10 to the power 2 means whatever that star that is at that level has an intensity 100 times the intensity of the sun. Correct? On the other side, here 10 to the power minus 2 means whatever the star at that level has an intensity, 10 to the power minus 2 means 1/100 of the intensity of the sun. That's how the y-axis works. The x-axis is just the temperature. So as you can see, there are so many points here. Each point is representing a star. Okay. So the pattern that you see is something like this. As the temperature increases, you see the intensity is decreasing for the stars that are in the main sequence. Okay, for the stars that are in the main sequence. What is main sequence?
The normal stars.
Normal stars. Now there's, okay, now I think I told you this last week also. That if you take a star, it has a life cycle. Okay, it has a beginning, it has a life period, and then eventually it has an end. Okay. So now for an example, if you take our sun, which is about 5 billion years old, 4 to 4.5 billion years old. It was initially started 4 billion years ago. And there is estimated lifetime that is remaining for the sun is another 5 billion years, another 5,000 million years. So at the end of 5,000 million years, according to science, this sun will not be there. So the sun will not be there means definitely the earth will not be there way before that. So anyhow, this sun has a life period of about 10 billion years. Out of that we are in the mid stage. We have always spent about 5 billion years. It will be there for another 5 billion years. Okay. So when the sun is initially formed, that's because of the gravitational forces. It collects the gravitational particles around it, the gases, and so it forms the sun was formed initially. The gravitational force works there. And then it started shrinking, it's becoming smaller, getting compressed. And then gravitational forces are trying to make the sun smaller. And then nuclear fusion, which is happening within the sun, which is the fusion of hydrogen nuclei, that gives an outward force. Okay? So now there are two forces involved. Due to the hydrogen fusion, due to the fusion of nuclei, there is an outward force, which is trying to make the sun expand. On the other side, there is gravitational force which is pull the particles inside the sun inwards. Okay, so the stage of the sun where these two forces are balanced is what you call a main sequence. Okay, that is what you call the main sequence. So simply, what is main sequence?
So what is balance?
outward force and the inward forces are balanced. Now let's say there is a spherical object, there are some people trying to pull it out. Okay. Another set of people trying to push it in. So now when these two forces are balanced, it's in some sort of equilibrium, right? That equilibrium stage is what you call the main sequence. Okay. At the moment, the sun is in that main sequence. But after a point, when the sun runs out of hydrogen, what happens is that outward force will reduce. When that outward force decreases, then what happens? The inward force by default becomes bigger. Then the sun starts shrinking. Okay, the sun starts shrinking. When the sun starts shrinking, the temperature will increase. So when the temperature increases, what will happen? This hydrogen fusion created helium will fuse. So when helium fusion happens, then there will be a huge outward force. And again, it will start expanding. Now, all of this is not relevant to you. If you want, I told you, you can read this in the O-level in Excel textbook, it's there. Okay, so or if you just Google, you just type life cycle of the sun, you can read all these details, what and what will happen, the sequence is given. Anyway, the main sequence means that stage where the outward force and inward forces are balanced. So that main sequence will be there for around 1,000 million years ago. I can't remember exactly. For some period, it will be there. So at the moment, we are in that period. Fine. Okay.
So, but can't the gravitational force also vary the force that compresses the sun?
Now, how can it vary when now gravitational forces will depend on the mass and the distance, average mean distance between the particles. So the mass is not going to change. And if by any chance if it starts getting compressed, if it compresses, then the gravitational force will increase. At the moment, no. Okay. Such a plot can give us some variable. Okay. Now, most stars we observe fall on a diagonal line across the Hertzsprung-Russell diagram, which is called the main sequence. These main sequence stars are stable stars which will exist in the state for the majority of their lifetime. Okay, the main sequence star are stable stars which will exist in this state for the majority of their lifetime. Their correlation represents the connection between brightness and high temperature. Note that the plot is always drawn with hotter temperatures on the left hand side. Oh, yes. Here the temperature is 20,000. Here the temperature is 10,000. Here the temperature is 5,000. Here the temperature is 2,500. So the temperature is increasing this way. For some reason, that's how it is given. Note that the highlighted part. Note that the plot is always drawn with the hotter temperatures on the left hand side. There are also other stages in a star's evolution which appear in other places on the diagram, but these are much shorter than its stable period. Thus, there are far fewer stars in those parts of the HR diagram. For an example, as blue supergiants burn out in just a few million years, most of these have already done so, and we do not see many. The top left area of the HR diagram is lightly populated. The top left area is lightly populated. Fine. So just know that this diagram gives you an idea about temperature versus the luminosity. And these stars are the stars in the main sequence. Okay, we'll see with questions what type of questions we get based on that. To the next one. Peak distance unit. That is not really important, but just read it. Just read this part.
So you said the sun gets compressed due to gravitational forces. Right? So then by the logic, can't Jupiter and Saturn and the gas giants also get compressed?
There should be some sort of equilibrium already existing. So depends on what other forces acting on those.
So then why do you only talk about the sun expanding and contracting like any gas giant can?
It depends on the mass and also the equilibrium. They are in already some sort of equilibrium. We don't know what are the other forces
So the sun's equilibrium is not that stable. Like it can change that.
for any stars. But it will be there in that stable period for some time.
So stars are much less stable than planets in terms of forces.
They are stable for a long period. After they run out of gas, yes.
Aren't the planets also run out of gas? Why not?
Because I'm not using
There is nuclear fusion happening in this. I don't think so. No, right? There's no nuclear fusion happening.
Yeah, but over time it can dissipate, right?
Yeah, possible.
That's I don't get why we are specifically referring to the sun and stuff.
That's because it's the boss. We are orbiting the sun. That's the reason. Okay, right. So guys, that astronomical unit we already met in a question. Just another unit to measure the distance. You can just read that. Okay. Then
So, yeah.
okay, guys, page 73. There's only a small one that we can answer. The question booklet is already mailed to you. Please check your email. The Hertzsprung-Russell diagram shows the relationship between luminosity L and the surface temperature T for a range of stars. The HR diagram below is for a young star cluster. Okay. For a young star cluster, you can see almost everything is in the main sequence star. Mark on the diagram the position of a star similar to sun. Similar to sun means it will have a luminosity ratio, the magnitude will be 1. So maybe somewhere here. Maybe something like, maybe this one. No, which has a relative magnitude of 1. The appearance of the HR diagram changes as the star in the cluster evolve. Explain the changes in the appearance of the HR diagram as the star cluster gets older. It's a 6 marker. We'll discuss that on the next class. Okay. Hold on. Long. Guys, page 66. Page 66, which is the part C of question 37. The sun is a yellow star with surface temperature of about 6000 Kelvin. In the 20th century, astronomers discovered a large variety of stars in our galaxy. Hertzsprung-Russell diagram developed as a way of classifying stars. An HR diagram is shown below. Label the x-axis of the HR diagram. You should include the approximate values. So, x-axis is temperature in Kelvin. And if I'm not mistaken, it's about 20,000 Kelvin here. You can check the diagram. Left end is about 20,000. Then 10,000 here. Then 5,000 here. And 2,500 here. Okay. The scale is not linear along the x-axis. Remember that. Neither along the y-axis. It's not linear. That is how it's labeled. You should include approximate values down. There are 5 zones, Z1, Z2, Z3, Z4, and Z5 identified on the HR diagram. Complete the following table. You should match one zone with each description. High mass hot stars, low mass cool stars, low mass hot stars. Again, wait a bit. I'll keep it for the next day. We will discuss that on the next day. And then page 47, question 27. You can easily answer the part D. Add a scale to the horizontal axis. So once again, 20,000 here, 10,000 here, 5,000 here, and around 2,500 here. Part B again, we'll keep it for the next week. Explain how the diagram shows that the cluster is not a young star cluster. If it is a young star cluster, it should be in the main sequence. So I can see a lot of stars not in the main sequence. That means it has gone passing its young age. Okay, more towards the dead end. You should refer to the groups of stars and their positions on this diagram. I'll keep it for next week. Right. So guys, let's continue from here on the next day. That's it for the day. See you next week. Bye. Sorry, I didn't get it.